Right, well, thank you very much. So, right, so this is the picture of Royal Holloway. It's, some of you might remember it for the British Combinatorial Conference, actually, in 2013. That's the last big combinatorics conference we had there. It's a Victorian college, 1885, I think it was founded. It's called Royal Holloway because it was founded by somebody called Thomas Holloway, who was basically a quack. He sold pills and ointments, but really was an early pioneer of advertising, right? So he built this women's college to advertise his good works on a hill over the railway, right? So there we go. All right, so what I'm going to talk about, something called non-overlapping codes. So I've worked with, we've done a few things now, but we haven't really talked about non-overlapping codes together at all. So I've sort of picked the topic really because I thought it would go down well. That's my hope. So it's an interesting topic, and I think there are still some really tempting conjectures out there that are reachable. That's, I guess, still interesting. So I guess first of all, I want to talk about non-overlapping. What is a non-overlapping code? So to do that, I really want to say what what overlapping means. So here are two words, binary words in this case. They're overlapping because you can see that at the end of one, the beginning of the other are the same. So you can kind of overlap them, and the portions that overlap match. Okay. So you can kind of think of them one written above the other, and there's an appropriate shift where they overlap. So so there we go. I also allow a code word to overlap with itself. So for example, trivially, let's say the all zero code word overlaps at more or less any shift. Okay. But I don't, to stop sort of trivialities, I don't allow a code word to overlap with itself completely, right? With no shift, right? Because somehow that's going too far. All right. So here's the sort of definition, right? So you've got two words, W and W dashed. They're of length n. They're overlapping if basically the end of one word is equal to the beginning of another, right? Right. So this is a suffix of one is equal to a prefix of the other, one way around or the other, and it should be a non-empty prefix and suffix. So there's got to be actually symbols in the overlap, okay? And it's got to be proper, so I don't allow sort of zero shift, right? That's what overlapping means. Okay. So for any pair of code words over some sort of alphabet, they're either overlapping or they're not. Okay. They might overlap in several different shifts, possibly. Okay. So all right. Well, what's a non-overlapping code? So here I'm thinking of all my code words are going to have length. They're all going to have length n, right? It's going to be a code word C, and they're going to be length n words over some sort of finite alphabet f of size q. Okay. So all right. Now I'm going to use that notation throughout. So so what is a non-overlapping code? It's non-overlapping if whenever you pick two code words, they don't overlap. Okay. So I'm allowed to pick the same code word. Yeah.
In your definition of code, is there any more structured than just a collection of words?
It is purely a subset of the collection of all words. That's it. Yeah, absolutely. Yeah. So there's no attempt there's nothing linear about them or anything like that. So, it buzzed. I wonder why that buzzed. Okay, so here's an example of a non-overlapping code, right? 3 binary code words here, right? Oh, hey, look at that. That's probably what's happened. It's buzzed because it's now switched this thing on. All right. So there's three code words, right? So I invite everybody to pick 2 code words, right, of their choice, maybe the same one. Do they overlap? No. No? Okay, great. So this is a distributed proof that this is a non-overlapping code, right? Okay. So, all right. And so what I'm interested in is obviously large codes. How big a code can we get that it's non-overlapping? Okay, so I'm going to call CNQ is going to be the maximum cardinality of such a thing, right? So I'm going to fix my length n, I'm going to fix my alphabet size q, and CNQ is just the biggest non-overlapping code in terms of cardinality. So what can we say about that? Okay, so that's the game. Right. So here is a construction of these things. So I'm going to fix some number k, right, smaller than n. I'm going to look at all the code all words of the form lots of k zeros, okay, and then with the next part of the word starts and ends with a non-zero alphabet symbol. So that's a single symbol, and then W is a maybe quite long word that sits in the middle of those 2 non-zero symbols. And what W has to have is it can't have k zeros in it, right? Consecutive zeros in it anywhere. Okay. So you can kind of see that if you take 2 code words of this form, they can't overlap, because if you take so if they do overlap, one of them will have the 0 end in the overlapping part, right? And there just isn't a way of sticking k zeros in this in that sort of overlapping part in any way, right? Even partially. Okay. So I call that word W just a 0 to the k free sequence, right? Because it doesn't have any zeros of length k in it. Okay. So this is due to, well, it's really a paper of Levenshtein in 1964. And he credits this to Gilbert, but in fact Gilbert had the same code, but used it in a different context, right? So so there we go. And in fact, this code here, this example, was an example of such a code just for k equals 2. So all the code words started with 2 zeros, okay, and they then have a 1 as the next symbol and the last symbol. The bits in the middle don't have 2 zeros consecutively, right? So if you want a proof that isn't distributed, that these things, that is an overlapping code, you can just say that, well, if they overlap, well, they can't overlap at one symbol because the end of because the 0 symbol will be the end of beginning of one code word and the end of another, and they can't overlap in more positions because there aren't any ways where there's no non-trivial way in which they can those 2 zeros can overlap, right, in terms of the positions. Okay. So there we go. So actually then, this is actually remarkably large, right? So the idea is that you can choose k to be what you want, and what you tend to do is you fix k to be, you let k to be quite small, let's say about log of n, right? So you think there's a small number of zeros, so when, for example, you have q about logarithmic in, when you have k about logarithmic in n, you have, you in fact have the number of code words is about q to the n over, well, in fact, 2en for q equals 2, actually here. This is true in general, but this 2en thing, this is when q is 2, which was said, right? So why is that? Well, you think fixing the first k symbols when k is about log n, that's kind of that's basically giving you this factor of n, right? Because you've taken 2 to the log n possibilities at the beginning of the sequence, and you sort of remove those, and then the 2 to the k, which is log n. So that gives you this n factor, and then this okay. So then the real restriction is this word w. So the point is that log n is long enough in terms of the bunch of zeros, so that the restriction on what w is going to be relatively small, relatively minor, right? It's quite a minor condition to be 0 to the k free when k is about log n, right? So the point is you've got these two balancing things, right? You have this as k gets bigger, you are making the code smaller because you're restricting very heavily the beginning of your code word, but you're making it bigger because you're making the conditions on w more relaxed, and that's why log n balances between these two things. Okay, so these things are big, right? So q to the n, that's the number of all code words, right? So you're saying basically about 1 over n, constant over n of all code words, at least when n is large compared to k, can lie in a non-overlapping code. So they're big, right? Right. So is this 1 over n an artifact of our construction, or should it really be there? Okay. And here's an observation that if you take any 2 cyclic shifts of a single word, right, they're going to overlap, right? Because I don't know. I hopefully you can see this in the online. But please complain if not. I don't know. Suppose I take I don't know 0 1 0 1 1. Take a cyclic shift 1 1 0 1. You can see that they can overlap, right? They're going to overlap. So if you divide up the collection of all q to the n words of length n over q into equivalence classes, saying 2 words are equivalent if they're cyclic shifts of each other, then we can only pick 1 code word from each of those equivalence classes. Okay, and how many equivalence classes are there? Well, here's my example. So the point is that the number of equivalence classes is about q to the n over n, right? The point is that each code word is most of the time is in n cyclic shifts, right? An equivalence class of size n. And of course, some words are going to be in a smaller equivalence class if they've got non-trivial periods, right? But most of the time, it'll be about this. So this says that non-overlapping codes can't be bigger than about q to the n over n, right? So that over n really should be there. So I guess the question then is, can we do better, right? Can we make these? Can we make it as close as 1 over n as a proportion? Okay. So I want to just give a bit of history and context first before going on here. So I guess the oldest thing of this type, I think, is something called comma-free codes. So what are comma-free codes? A comma-free code is if you take 2 code words and concatenate them, right? You're not allowed to have a code word in the middle, right, at all, anywhere. Right, the only place where a code word appears is at the end or the beginning, right? That's comma-free code. And these are also known as self-synchronizing block codes. And you can kind of see why the self-synchronizing thing is happening here. Think of you broadcasting a collection of code words from your code. and you just concatenating them into a stream, and the stream goes out. And if you're not synchronized with this stream, you just come in late. You want to be able to break this up into chunks of size n that are code words and start decoding your stream. And this self-synchronizing property allows you to come in late and realize where code words start, right? So you can carry on. You only just miss the beginning of the sequence. So this is the self-synchronizing. And in fact, actually, though, they were originally motivated by trying to understand how DNA encodes proteins, right? So the first paper on this was Crick, Griffiths and Orgel in 1957. So that's the famous Crick, right? Right, Crick and Watson Crick. And Goleman, Gordon and Welsh had a paper in 1958, very nice paper. And then there was an amazing paper by Eastman in 1965, actually. So it turns out that, amazingly, there's this paper of Eastman which basically says that if n is odd, then, oh, and I should say that the bound that we got in terms of q to the n over n, that works for comma-free codes, it doesn't just work for non-overlapping codes. And amazingly, when n is odd, that bound can be achieved, right? So you can pick one code word from any a full cycle, and you get a code that's of maximum size. It's still not known enough, I believe, what the maximum size of such a code is when n is odd, when n is even. Okay. So okay. And then we have non-overlapping codes, right? So, and these are known as strong comma-free codes, partly because they are a type of comma-free code. With if you look at it, it's got it's a stronger condition than the comma-free property. But they've also got other names, mutually uncorrelated codes or MU codes. That's what comes from the biological, the sort of DNA type literature. You can see, okay, so uncorrelated doesn't mean what an information theorist might think of as uncorrelated, right? It's not that kind of correlation, but they're sort of thinking that of the overlapping is a kind of correlation, right? So they're uncorrelated if you can't overlap them. And there's also another synchronization application where quite a few of the researchers call them cross-bifix free codes, actually. So, and you can kind of see why. I mean, bifix to do with suffixes and prefixes, and see why they're called that. And actually, this last application was how I got into the thing, actually. There was a lovely paper by Yaming Chi and some co-authors that I read on this kind of topic. It got me into the area. So they're a common free code with some sort of extra property. It's got a decoding automaton. And these were introduced, again, quite early. They were introduced by Levenshtein in 1964, hence that construction 1. And he came back to it in 1970, and they've been applied by various people. Jim Massey in the 70s, Nielsen, Gribas and Oglivsko, that's to do with pattern matching, these kind of things. You can see that they're useful for synchronization applications. So if you're an applied, motivated person, then synchronization. Think of synchronization. And there've also been more recent twists on this thing. And one thing that I should say, there's several of these things. Here's just one I thought I'd pick up. There's something called circular codes, which are Arquez and Michael in 1996. Again, motivated from the DNA perspective, where here your condition is that if you take any cyclic concatenation of code words, there's only one shift that decomposes into code words, right? You can't decompose them in a different way. Okay. Okay, is that okay so far? Yeah? Okay, great. So, so here's Levenshtein's conjecture. He gave him his paper in 1970, which is that construction 1 is always optimal. That's the best you can do. Okay. Yes.
Can I ask another question?
Yes.
Do you mean optimal exactly or optimal asymptotically?
Well, I believe, yeah, optimal exactly, I believe. He said optimal. Well, I assume that's optimal exactly. But, yeah. Yes. He certainly didn't talk about an asymptotic regime or anything. So I reckon it's optimal. So here's from some data for Q equals 2, the binary case, by this paper that I got into the area with by reading by Chi, Kier, Perkayasta, and Wang from 2013. This is IEEE Transactions Information Theory paper. And here I've listed small values of n, and this is the largest binary non-overlapping code of length n, right? And so this is really, actually, I think this is really great that you could go this far, right, by searching. This is a computer search, and this is by using sort of a clique finding algorithm. It's amazing what you can do with clique finding algorithms, I feel, nowadays. And if you compare this to the construction 1, Levenshtein, the Gilbert-Levenshtein construction, Gilbert-Levenshtein achieves that bound, right, for all of these values. Except n equals 9. That's why it's in red. So there is a construction that achieves 14, whereas 13 is the best you can do for the Gilbert-Levenshtein construction. So it doesn't quite get there for n equals 9. So that kind of, well, I don't know. Does it make you more or less doubtful about the, well, the conjecture clearly doesn't hold, right? There's this single example, but are there any other counterexamples? I mean, these are small numbers, aren't they? So there we go. So what was that construction? There's a paper of Bellotta, Pergler, and Pinzani, 2012, which gives it gives an infinite family of constructions, but you'd expect the family to be poor asymptotically. So so you wouldn't expect this construction to. I don't think it beats the. Certainly doesn't beat construction 1 for other parameters, but this for n equals 9, it is best. Okay. Okay. There's not anything else to say. Yeah, okay. So here is a better upper bound on for non-overlapping codes than one that comes from comma-free codes, right? So this is it's a factor of 2 better, right? So the bound to do with just cycles that gave you about q to the n over n, and this is q to the n over 2n, right? So I've slightly cheekily called sort of quoted myself in this paper, but really, Chiatal, that's their bound. The reason why I've quoted myself, well, there's 2 reasons really. First of all, because my bound actually is the inequality is strict, right? And theirs wasn't strict, okay? And secondly, actually, the proof is my proof, right? So the proof in the Chiatal paper was expected you to know about a particular synchronization application. It was coming out of that application, right? So this is a purely combinatorial proof. So how does it work? Well, as I tell my undergraduates, you know, combinatorial is all about counting things twice, right? So, what the trick really is to find out what to count twice. So here it is. You take the collection of pairs X, where the first element of the pair is a word, but it's a word of length 2n minus 1, right? It's a longer word. And you think of the word being written in a circle, right? and the second is a position I on that circle. Okay, so these are the two things we're going to count. All right. So, and the condition that you need to have is that if you start at, so if you look at this circle, this W written on a circle, and you start at position I, and you sort of move around for n of those 2n-1 positions, you get a code word, right? That's the condition. So I'm picking a non-overlapping code C first, and then constructing the set X. I want to show that the number of code words is at most q to the n over 2n-1, right? So that's what I'm counting. So how does the so here it is. Suppose, for example, in my previous example, I had 001101 as a code word in my code. Then here's a typical element of X. I've written a bunch of longer words of length. Well, so what was it? 1, 2, 3, 4, 5, 6. So this was length 6. So this will be a word of length 11, hopefully, right? 2n-1 in the same alphabet. And I put a comma 8 here because if you look at position 8, which is this position here, and you count round, it will have this particular code word here, 001101. Okay? So I'm counting things like that. So okay, so I count once. What is the size of this set X? So what I could do is I choose my position, right? I then choose a code word to start at position I. Okay, I've got the size of C possibilities for this. And then I choose the remaining n-1 positions. Okay, so this is the size of the set X. And the second way of counting, right, I first of all choose my sequence W, right, written in a circle. So there's q to the 2n-1 possibilities for this sequence. But at some point in the sequence, I need a code word, right? So whatever it is, it's not any of the q constant words, because if it's got if you've got just the same symbol written over and over again, no matter where you start for where your code word is going to be, it's going to be the constant word, and then the constant word is never going to be in your code because it overlaps with itself, not trivially, right? Right, so it can't be part of an overlapping code. So we can't find a position I for those particular Q code words. So there's at most Q to the 2n-1 minus Q possibilities for W. Okay. And then there's at most one possibility for I. Because if there were two possibilities, right, so here we've got a circle here, right, of code word of W written circularly of length 2n-1. So if there's two places where a code word starts, right, because these code words have got length n, and we've only got 2n-1 positions, that means that they would have to overlap, right, if there's two places where a code word starts. Okay, and that's not allowed, right? So you can only fit one code word in a circle that length. Okay, so there it is. So it's at most q to the 2n-1 minus q. Oh, okay. So that says that 2n-1 times the size of the code times q to the n-1 is at most q to the 2n-1 minus q. You divide both sides by an appropriate thing, and you get the result, right? Okay, right. Just using the fact this is less than q to the 2n-1. Okay. Okay. So there we go. So that's a sort of simple bound. So that shows that the biggest non-overlapping code is certainly not as big as the biggest comma-free code, for example, at least for n-odd. Right. So they are different objects. Okay. Okay. So this is the sort of generalizing that argument, and this is well, Well, you meant to put 2022 plus on for things that aren't published, right? But I'm not expecting to publish this because it's really a failure, right? But I mean, the result's there, it's true. And I'll say why it's a failure in a second, but it's an interesting failure. I think it's got a lesson to teach us all, right? So this is a generalization of this. So I'm taking so rather than looking at things written in a circle where there's 2n-1 positions, I'm just picking a big number, capital N. And actually I'm looking at sequences rather than things written in a circle, just because things are just easier to do. And I'm trying to count the number of C-free sequences of that form. So C-free means they don't have a code word that occurs anywhere in them. Okay. So there's so you can kind of see, okay, so how would you count such a thing? You count it using an inclusion-exclusion argument, right? You have some bad events, which is that your code word appears at position I in a sequence, right? And then you do an inclusion-exclusion argument. How does this work? Well, you know, the -1 to the m is that m is how many m code words are appearing in the sequence. You've got this sort of power of -1 that's sort of showing as an inclusion-exclusion argument. And then this is a sort of a counting thing. This binomial comes from so how do you count? So if you've got, let's say, m positions, and you know your code words appear in those starting points, you first of all choose those code words. You then need to sort of say, well, where do they occur in the sequence? So you choose some integers, which are the gaps between the occurrences of the sequences, and that gives you a binomial coefficient, right? But there you go. And I've pulled out. I've pulled out a factor of q to the n. So if you ignore that first factor, that's just the proportion of C-free sequences that there must be. And the point is, though, that if the size of the code is too big, this ends up negative, right? So it does give you a bound on the size of a code. So the idea is if a code is too big, you let capital N be very large. As it goes off to infinity, you get a better and better bound actually for the code. Right. So why was I interested in that? Well, it's because of So the point is that it does give you a bound on C. Why was I interested in that? It's because actually this is just a counting version of an old bound. And this is a bound, very beautiful bound, due to Levenshtein again in that 1970 paper, which is that so here we've got the q to the n over n factor here, like the upper bound, and then we've got n-1 over n to the power n-1 in front. Okay, so this is definitely less than q to the n over n. So in particular, for example, when n is extremely large, this thing at the front becomes about 1 over e, right? So this is q to the n over e times n, right, for n large. And hey, our construction, right, the Gilbert-Levenshtein construction, asymptotically was about q to the n over 2en, right? So the fact there's a nice factor of 2 between this upper bound and lower bound, I think it's really makes you think, well, what else can you use to improve this bound or to improve the construction to make these things tighter? A factor of exactly 2. So how does this work? Well, it's essentially this C-free sequences argument. He just produces a recurrence for the number of C-free sequences, and then uses a bit of algebraic combinatorics, bit of power series manipulation to derive this bound on the size of a non-overlapping code, right? A very beautiful bound, actually. So in some sense, well, okay. So really, you should really, for the moment, definitely ignore that top bound. It's really Levenshtein's bound, right? Okay. But you see what's going on when you fix n and let q tend to infinity, for example. Okay. Well, so as a proportion of q to the n, this upper bound doesn't change, right? It's a function of n only, right? But our construction 1, actually behaves really poorly when we go off in that direction. Why is that? Well, as soon as we fix the first element of a sequence to be 0, which we do in this construction, that's already removed all but 1 over q of the possibilities, right? So if q tends to infinity with n fixed, the proportion of code words in our code tends to 0, right? Whereas this upper bound, this proportion is just a fixed number. So the construction 1 is way off this upper bound when q is fixed and n tends to infinity. Okay. Okay. Yeah. So we need another construction actually, which gives us a better bound for that kind of situation, right? Where we've got large alphabet size and small length. And here's a really simple construction, which achieves this. So I take my alphabet. So now I'm thinking of my alphabet as being big, right? I take my alphabet and I divide it up, partition it up into 2 disjoint sets, right? S and B, S for small and B for big, right? And the small elements are going to be about 1 over n of all the things in the alphabet. And the big elements are the remaining n minus 1 over n elements. Okay. And then I take the code word, which consists of small element followed by n minus 1 big elements. Okay. So the point is here, there's no way that these are going to be overlap non-trivially because a small element will be against one of the big elements, right? If there's an overlap, okay, and S and B are disjoint. So yeah. So how big is this? Well, okay. So I've got about 1 over n times q choices for the first position, and about n minus 1 over n times q choices for the remaining n minus 1 positions. So the size of this code is going to be, well, when n divides q, it's going to be exactly n minus 1 over n to the n minus 1 times 1 over n times q to the n, right? Okay. But that's the upper bound due to Levenshtein. Okay, so actually I had to sort of check this about 10 times really when so it shows that actually the Levenshtein bound is tight whenever n divides q. Okay, so and this really shows that construction 1 is nowhere near optimal, right? Because you've got much bigger optimal versions for large alphabet sizes. Okay, very simple construction. So right, so there we go. And what was I doing in 2015? I was actually able to show using these kind of constructions that in fact there's an absolute constant c such that the size of c in q is at least q to the n over c times n, no matter what n and q are. Okay. So that really says that no matter what your parameters are, you expect about 1 over n of the code words to be in your code. Right. So in order to do that, you needed a construction which is a bit more general than that. I should explain, maybe I'll explain it in 2 parts. You can combine construction 1 and construction 2, right? So you take construction 1, these are 1s and 0s. You now, rather than 1s and 0s, you think of big and small. Okay. Then you get constructions which are much better for any collection of parameters. The problem with that, just doing that construction, is there are weird situations to do with rounding errors, right? Where, like with construction 1, you're choosing this value of k, and it might be that because k has to be an integer, and you want it, let's say, to be log n, you can't choose an integer that's sufficiently close, so you get something that's slightly wrong, right? So to cope with that, what you actually do is, rather than assert that the first k things must be small, you just take a large subset of the collection of all length k words over a small alphabet, right? And say it's got to be in that large subset. And then say that this word W has to be that subset free, okay? And that's enough. You've got plenty of room there to prove this, okay? Okay. Right. So, so here are some conjectures, right? Or questions, really. So in particular, the most tempting question is the Gilbert-Levenshtein construction optimal? So if you fix just for binary alphabet, let the length n tend to infinity, we know it goes wrong to 1 off best for n equals 9. What happens for larger values of n? And I mean, with Jonathan's question about asymptotics, right? The asymptotics, the proportion is the upper bound is 1 over e times n as a proportion. The lower bound is this construction, which is 1 over 2e times n, right? So is it the case that that there is an argument which doesn't involve C3 sequences, involves something else, that drops the upper bound by a factor of 2, right? Or is there a trick for large values of n that allows you to get this extra size of code, right? I mean, that factor of 2 between upper and lower bounds, I think this makes this a frustrating but very tempting question, right? So there we go. And you could even ask for other alphabet sizes. So if you fix your alphabet size to be q, and you let the length tend to infinity, so in other words, the length becoming sufficiently large, is it the case that this construction 1 is optimal? Right? It has a feeling that that's what it should be, actually, but I don't know how to prove that. So in the other option, the other direction, if you fix a value of n, if you fix your length and you let your alphabet size q tend to infinity, is it true that this second construction that I put up is an optimal one, right? And that, again, might well be true. So sort of for these kind of things, I guess you're wanting, certainly in that first case, you're wanting an upper bound that really depends on q as well as n. So the Levenshtein's upper bound is q to the n times something, where that something is purely a function of n, right? And if you're going to improve this, for example, if you can prove that first conjecture by showing that the Gilbert-Levenshtein construction is optimal, you need an upper bound that really depends on that alphabet size q, okay? So this is really why I was interested all this way back in this result here, right? The question is it that the way that Levenshtein used asymptotics to count the number of C3 sequences, the contradiction that he produced, was it that somehow the way that was done somehow removed any dependence on Q, right? Or not? And the annoying thing is, if you actually count, so the point is that the theorem here, that top result, is a non-asymptotic. It's a precise counting result, and you can kind of see the way that I've written it as a proportion of q to the n. Everything outside that sort of bracket, which is the powers of n, it's always a function of n only. The q doesn't appear outside there, right? As a proportion, right? If you remove that q to the n on the left-hand side, and if you think of this is what you're trying to optimize, size of Q over Q to the n. This sum here, there's no dependence on Q, right outside that proportion. So that says that in order to produce a better upper bound, you can't try to derive your contradiction just by looking at C-free sequences. Okay. So that's why I was interested really in this theorem. And that's the lesson it has to say, right? You need to improve the upper bounds. What you can't do is just try to be cleverer about counting C-free sequences. You really do need a different idea. Okay. There he is. Okay, so so this is really a question. Is there an improved upper bound on CNQ over Q to the n that depends on Q in some way? Yes, that's the question. So so there we go. Well, so so I kind of chose this topic, as I said, because I hope Doug enjoys it, and I hope that people have enjoyed learning about it. But I should say happy birthday to Doug. So and I should also say what a wonderful place this is. I'm so glad to be invited. It's such a wonderful place to be. It's lovely to see everybody again. Actually, it's really wonderful. So thanks very much for this opportunity, and yeah, and thanks.